problem 15, we needed to find the sum of all solutions to that equation. This problem, I think it is the easiest one in this exam. And when we see it's square root within square root is something not that simple, we can consider substitution. Let y equals the square root x squared plus x plus 7, which implies that x squared plus x equals y squared minus 7. So the equation becomes y squared minus 7 plus y equals 5. Or if we rewrite it, y squared plus y minus 12 equals 0. We can factorize it easily. Y plus 3 times y minus 4, which is 0. And the only possible y is 4 because y is a square root. It cannot be negative. And we have x squared plus x plus 7 equals 16. X squared plus x minus 9 equals 0. This is the quadratic equation. We don't need to find the specific x because we have the Vieta's formula, which tells us that the two roots equals negative b over a, where b is 1, a is 1, so it's negative 1. The answer is B. Problem 16. As shown in this picture, there is a small solid semi-ball, and there is a larger hollow semi-ball. The small semi-ball is inside of the larger semi-ball, and the diameters are given 1 and 2 respectively. We want to find the largest solid ball that we can put inside of the semi-hollow ball. To make it the largest, the solid ball needs to be tangent with the base or the bottom. It also needs to be tangent with the other two semi-balls. Okay, whenever there's tangent, it is useful to look at the centers of the ball or semi-ball. Okay, so let's connect them. Let's assume that the radius of the solid ball is r. We don't know it. We want to find the largest possible value. And the radius of the small one is 1. And let's also connect the center of the solid ball and the large hollow ball. So what is the distance? We know that the radius of the large semi-ball is 2, and this is r. Therefore, this part must be 2 minus r, right? So it is 2 minus r. And this piece, it is 1. We know it already. Now, because tangent, we know that the height is also r. This is the piece that we don't know. Let's call it x. If we look at the distance between the small semi-ball and the solid ball, the distance is r plus 1, and it is also the hypotenuse of a right triangle. The squared equals the sum of the squared of the two legs, which is x plus 1 squared and plus r squared. So this one, this is a larger one. Okay. Next, we have the green one. Let's focus on this green triangle. Again, we know the hypotenuse, which is 2 minus r. We square it. It equals x squared plus r squared. Okay, we have two variables and two equations. Let's subtract them because we see that both of them have r squared. We have the left-hand side, the r squared are canceled. We have 2r minus 4r, which is 6r. And we have a 1 minus 4, which is 3, equals x is, for the right-hand side, x squared are canceled. We have 2x plus 1, which means that x equals 3r minus 2. Now, we have this relationship. We can substitute it to any of them. Let's say that we substitute the x in the second equation, which is 2 minus r squared equals 3r minus 2 squared plus r squared. You can use any other tricks to solve this problem, but let's just do step by step. We have r squared, we have negative 4r plus 4, 9 times r squared minus 12 times r plus 4 plus r squared. Things are canceled, 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 canceled. So we have 9 times r squared minus 8 times r equals 0, which means that r is either 0, which is not possible, or 8 after 9. So the solution is 8 after 9. Problem 17. If 6 solutions of that equation form an arithmetic sequence, what is Q? So we are told that it is an arithmetic sequence. Basically, we can use 2 values to express an arithmetic sequence, right? We can use A and a D. So let's just write down the 6 numbers. Let's start from A, then we have A plus D, A plus 2D, A plus 5D. There are only 2 unknown values. The problem is that we don't have a lot of information from the equation. It doesn't seem to give us a lot of information. But if you're familiar with a polynomial, you will see that, okay, the highest order is 6. Although it's not shown here, but for the 5th order, the coefficient is 0. Although it is not written there, but it is 0, right? The coefficient of x to the power of 5 has a coefficient of 0. So that is also used for information. Next, we see that we know we are able to express the solutions using A and D, but we have to find some information so that we are able to compute A and D. So as I said, if you look at the 5th order, the coefficient is 0. How is that related to the question that we want to solve? That is the Vieta formula for polynomials. Okay, let's look at a general situation. We start with a n x to the n plus a n minus 1 x to n minus 1 a 1 times x and a 0. This is a polynomial of order n. It equals 0. If we look at this equation, the Vieta formula tells us the sum of different combinations of the roots. So let R1, R2, Rn to be the roots. The Vieta formula tells us that if we look at the sum of the solutions, it equals negative an minus 1 over an. If we look at the multiplication of all the roots, it equals negative 1 to the n, a 0 over an. Okay, so let's see what it is in this situation. So in this situation, n is 6. In our situation, n is 6, and an is 1, and a 5, which is an minus 1. An minus 1 is 0. And we also have a 0, which is negative 2 to 5. So if we plug in here, it is 0. And this one, it is negative 2 to 5, right? But we can also use the A and D to express them. So this one is 6A times 1D, 2D until 5D, which gives us 15D. And this is 0, which implies that A equals negative 5 over 2D, right? And then this one, because we already know that A equals negative 5 over 2D, this tells us that we can rewrite this to negative 5 over 2D plus D negative 3 over 2D plus D negative 1 over 2D, and then D over 2, 3D over 2, and 5D over 2. If we multiply them together, we have 3 negatives. So it's negative, and then we have a 15 squared and over 2 to 6, D to 6. So from the second equation, we cancel 2 to 5, we cancel the negative. That tells us that D to the 6 equals 2 to the 6, which means that D is 2, right? Okay, now D is 2, which means that the roots are, in fact, it can also be negative 2, but you will see that they give you the same solution. Okay, now we have D equals 2. So what are the 6 solutions? If we plug in, so we have a negative 1, negative 3, negative 5, negative 3, negative 1, and then we have a 1, 3, 5. So the polynomial x, let's go back, x to the 6 plus is q times x to the 4th plus p times x to the 2nd minus 2 to 5. So this one, it equals x plus 5, x plus 3, x plus 1, x minus 1, x minus 3, x minus 5. We see that we have a plus b times a minus b, x squared minus 25, x squared minus 9, x squared minus 1. So we are looking at q. Sorry, I think I messed up p and q. So this one is called p, this one is called q. This is q, this is p. We are looking at the coefficient of x squared, which is p. So how can you get x squared? So each time you only choose one, and the other two you need to choose constants. So p equals 25 times 9. You choose x squared from the last item, or if you choose x squared from the second item, or if you choose x squared from the first item, then this gives you 259. The answer is D. In the previous method, we used the two variables A and D to denote the arithmetic sequence. Note that this polynomial function only has even powers, which means that if we have 3 as a root, then negative 3 must also be a root. Okay, so let S be the one with the smallest absolute value. Then negative S must also be a root, right? So the difference is 2s, which means that the next one should be 3s, and then the next one is 5s. And this side we have negative 3s and negative 5s. Now let's use the Vieta formula for the product of the roots. the product of the roots, if we multiply them together, let's multiply them together, we have negative 15 squared s to the 6th power, which is negative 225 x to the 6th. This one, by the Vieta formula, a equals negative 1 to the power of 6, because the highest order is 6, and negative 225 divided by 1. So this tells us that s to the 6th is 1. So s could be negative 1 or positive 1, but it doesn't matter because we don't care about, the order, whether it's descending or ascending. So let's say that s is 1. With that, we have negative 5, negative 3, negative 1, 1, 3, 5, with being the roots. Okay. And with this, we can rewrite the polynomial function to x squared minus 1 times x squared minus 9 and x squared minus 25. This one equals x to the 6th plus p x4 plus q x squared minus 225. So we need to find the coefficient of x squared. If we take x squared from the first item, if we do from there, then we have negative 9 times negative 25. If we take from the second item, then we have coefficients negative 1 times negative 25. If we take x squared from the third item, we have negative 1 times negative 9. Add up the three numbers, we have 10 times 25, which is 250 plus 9. So the result is also 259. Question 18. This is a super interesting question. We are going to show 3 methods to solve it. I used the last 2 methods. They either involve trigonometry or some algebra. The first method, I call it method 0. This is from a book. It is super simple that you see that it doesn't require very messy calculation. Okay, to give you some hint, can you find a pair of similar triangles in the picture? There's one pair that is congruent. The pair that I mentioned, they are not congruent, but they are similar. You might want to pause to see whether you can find them. Okay, now I give you another hint if you haven't found it. They are A prime, B, E, and F, C, A prime. Let's see why is that. We know that both B and C angles, they are 60 degrees. They're the same, right? Okay, let's look at angle CA prime F. And this one, if we add A prime FC, then add 60 degrees, we know that this is 180 degrees because they are the 3 angles of the triangle A prime FC. Now let's look at this one. If we add CA prime F and FA prime E and EA prime B, it is also 100 degrees because this is they form a straight line, right? And also this one, in this one, they are the same because you fold it. So it is 60 degrees. 60 degrees, 60 degrees, 60 degrees, 60 degrees. Thus, this part, we can replace it with 60 degrees. From these two equations, we can conclude that the angle A prime FC and EA prime B are the same. A prime FC, let's use red color, which is this one, and EA prime B, they're the same. So we have two pair of angles are the same among these two triangles, which tells us that the triangle A prime B E and F C E, they're similar with each other. Once we know two triangles are similar with each other, we would like to know their ratio in terms of a side length, for example. We know that this is 2, this is 4 is given because the side length is 6 and the ratio is 1 to 2. But this doesn't tell us enough information about the ratio of these two triangles. Is there another way that you can find out the ratio of the triangles? How about perimeters? Can you find their perimeters? We notice that this AE and A prime E, they're the same, right? So which means that A prime E plus BE equals AB, which is 6. Thus, the perimeter of this one, the perimeter is 6 plus 2, which is 8. And similarly, this one, the perimeter is 6 plus 4, which is 10. So now we found the ratio of the two triangles in terms of side lengths or in terms of perimeters. Okay, so next we're going to use this information to find out the length of BE. Let's erase information that we don't need anymore. Okay, we want to know BE, so let's look at the ratio of BE. BE corresponds to A prime C, which is 4, and this equals the ratio of the two triangles, which is 8/10. Immediately, we know that BE equals 32/10, which is 16/5. Next, we're going to introduce two more methods. As I said, one involves trigonometry, the other one involves more algebra. So I think the for method 0, it's very simple. The calculation involved is not a lot, but probably it's not easy to come out with this idea. Problem 18, we have an equilateral triangle ABC, side length 6. We have E and F. We fold ABC along EF so that A falls on the point A prime on BC. And we also know the ratio of BA prime to A prime C, which means BA prime should be 2 and A prime C should be 4, right? Okay, so what is BE? We don't know it. Let's just put it X. And the total of AB is 6, so AE is 6 minus X. Because we fold A and let A fall on A prime, which means that AE and A prime E should be the same. So this should also be this should also be 6 minus X. Now look at this angle B. It is not any arbitrary. So this is from an equilateral, which means that it is 60 degrees, right? This is so special. And also we know that A prime BE, we know the 3 side lengths. I mean, 2 of them are functions of X. So we have 2X, 6 minus X. So if you know cosine theorem, that would be very easy. If we use cosine theorem, that says that the cosine of B which is 1/2. So this should be the square root of x plus the square root of 2 minus 6 minus x squared, then divided by 2 times x. Okay, so if we cross 2, what we have is that x squared plus 4 minus 36 plus 12x minus x squared equals 2x. 10x equals 32, x equals 3.2, which is also 16/5. So this is method 1. If you know cosine theorem, this is really easy. So this one, in the cosine theorem, it connects the side lengths to angles. If you don't know it, that's fine. Let's look at method 2. In method 2, again, I know that this is 2, this is x, this is 6 minus x, this is 6 minus x. And angle B is special, it's 60 degrees. I want to take advantage of that. I know that it works best if I have right triangles. So if I draw the height of this triangle A prime B with base A prime B, so the hypotenuse is x, so the shorter leg is x over 2, which means the other piece is 2 minus x over 2, and the height, the longer leg is square root 3 over 2 times x, right? So, but we also have another right triangle, and now all the side lengths involve x, and it's right triangle, which means that the square root of the hypotenuse equals, now sum, equals the square root of one leg plus the square root of another leg. If you solve it, again, you're going to have a linear equation, and x is 16/5. This is method 2. Even you don't know it, you take advantage of 60 degrees, construct right triangles, you can still solve the problem. Problem 19, this is about a function. Although we don't know the specific form of this function, but we are given an alternative form. So ideally, we would like to see fx in terms of x. But here inside f, we are given xy plus 1. And also we know that this relationship holds for all real values of x and y. With that, we can try some special values so that we can get a better understanding of this function. We notice that if we let y equals 0, then the right-hand side, we're going to have fx times f0, but f0 is 1, right? So that will give us more information. So let y equals 0. In this situation, we have f1 equals fx times f0, which is 1, and minus f0, which is 1, and then minus x, then plus 2, which means that fx equals x minus 1 plus f1. So if we know f1, then the problem is solved, right? We are given f0. How can we get f1? Again, we want to try special values. So we notice that if we let both x and y be 0, and the left-hand side we have f1, the right-hand side we have f0, which is 1, f0 is 1, minus f0 is 1, minus 0, and plus 2, which is 2. So combine them, immediately we obtained fx, which is x plus 1. And now we are given that fa is 2020, but fa is just a plus 1, which means that a has to be 2019, right? So this problem is not as difficult as you imagine. Although I know that it's a function, a lot of time problems involving function can be tricky. Question 20. How many two-digit numbers x satisfy this condition? There are many ways to solve this problem. Some of them involve more algebra than others. In the first method, we are going to use some reasoning to narrow down the number of x's that we want to check. And after that, it is a check and guess game. Okay, let's start from writing down the condition. X squared minus 10x minus 22 equals the multiplication of the two digits. Let's say they're a and b. We know that a and b, they are digits, right? So the multiplication is no greater than 81. And this implies that if we move the constants to the right, x squared minus 10x less than or equal to 103. If we rewrite the left-hand side, we have x times 10 minus x less than or equal to 103. This implies that x has to be no greater than 20. Thus, we don't need to consider all two-digit numbers. We can only look at the numbers between 10 and 20. So let's write the condition one more time. We want x times 10 minus x equals 22 plus ab. If x is 10, then we have 0 equals 22 plus 1 times 0, which is incorrect, right? 11 times 1, which is 11, equals 22 plus 1 times 1, also incorrect. 12 times 2 equals 24. 22 plus 1 times 2. This one works. Let's do 13. 13 times 3, 39, equals 22 plus 1 times 3. This is impossible, right? This will not work. And also, you realize that the left-hand side number is getting larger and larger, but the right-hand side, it is no greater than 10 because a is 1, or I mean, no more than 2. You can stop here, or if you want to make sure, you can check the remaining numbers no greater than 20. So you will see that 12 is the only case that works. So the choice is B. Next, we're going to introduce another method which involves a little bit more algebra. Specifically, we are going to use the root formula of quadratic equation. How many two-digit numbers x satisfy px equals x squared minus 10x minus 22, where px is the product of the two digits? Let a and b be the two digits, that is x squared minus 10x minus 22 equals ab. And if we rewrite this to the standard quadratic equation, we have x squared minus 10x minus 22 minus ab equals 0. So x has to be integer, so the coefficients has to satisfy some conditions. Let's look at the roots. We can use the root formula. X equals over 2, 10 plus minus b squared minus 4ac. 100 plus 88 plus 4ab. And we cancel out the 2. We have a 5 plus minus 47, 22 plus 25, which is 47, plus ab. Within the square root, it has to be a squared number. And we also know that a and b are between 0 and 9. So it cannot be more than 47 plus 81 within the square root. Basically, what we need to look at, we needed to check all the square numbers between 47 and 47 plus 81 to see which of them would give us a b, so that we can find the integers of a and b. For example, the smallest one is 49, which means AB equals 2. It works. We can let A equals 1, B equals 2, or A equals 1, B equals 2. And if you check 64, 64 minus 47 is 17. You cannot find the A and B digits such that the multiplication is 70. If you check all of them, you find that AB equals 2 is the only option, which means that A equals 2, B equals 1, or A equals 1, B equals 2. For the first one, it gives us 21. For the second one, it gives us 12. Do both of them work? We see that, let's just check. If x equals 21, within the square root, we have 5. We need a 5 plus 16. But in the square root, it cannot be 16. How about the second one? So this one works. When x is 12, 5 plus 7, we need 7, which is exactly. So the answer is 1. There's only one such x. B.